there. Got a line. And between these two, so there and there, got a line. And those three actually goes through 1 point, which is cool. Now, I need someone to prove that they all go through 1 point. Okay, someone who hasn't spoken before. I'm going to give you a pointer. Okay. So usually when you want to prove that three lines are concurrent, okay, what's up?
So if you, for example, name the circles A, B, and C.
Okay, A, B, and C.
Then that 1 point over there, if it has the same power for circles A, B, and AC, then it has to have the same power for all three.
Yeah, pretty much what he said. Okay, so the way it works is, let's say A, B, A, C, let's delete this one. Okay, so works like this. When you want to prove that three lines are concurrent, one way of doing it is to just intersect two of them and then prove that that intersection point also lies on the third line. So we can do it here. We can just intersect two of them and we don't know that the other one. So we intersect that one, let's call that L, M, and N. And this point, what are we going to call it?
Omega.
No, let's keep O for centers of circles.
Omega.
Omega. Okay. Omega it is. Wait, like lowercase omega or capital omega?
Capital.
Capital, okay. So, capital omega. So, omega has the same power with respect to A and B. Why? Because it's on the radical axis of A and B. It has the same power with respect to A and C, because it's on the radical axis of A and C. So, so power of omega with respect to A is the same as the power of omega with respect to B, but it's also the same as the power of omega with respect to C, because it's on that line. So therefore, these two are equal, so P or omega must lie on this line, which is the radical axis of B and C. Cool. That's cool. Now, what if the circles don't intersect? Anyway, sorry, just a little bit of terminology. So radical axis is the line, radical line between two circles. Omega here is called the radical center. Cool. So that's cool. Now, let's see what happens when your circles don't intersect. Ooh, by the way, before I do that, you've got two circles, and let's say they intersect. You've got your that is a circle. Okay, you've got your radical axis, which goes through those 2 points, but you've got points which are inside both circles. How do you define the radical, or the power of a point that's inside the circle?
Negative.
Well, it's kind of in the same way. Let's say that's point P. We draw a line through point P. That's A and that's B. The power is PA times PB. So it's basically the same. Only difference is that when you have a point inside the circle, the power is negative. Why should it be negative?
Because if it's on the circle, on the circumference, it's 0. On the outside, it's positive, so inside should obviously be negative.
I mean, it could be like positive and then 0 and then positive again. There's nothing stopping it from doing that. Okay, someone, everything is good. Okay, what's up?
Using directed line segments, because when it's outside the circle you go PA and then you go PB is in the same direction, whereas in here PA is going one way, whereas PB is going the other way. So then one of the lines is in directed line segments is going to be a negative one.
Okay, cool. So one way to do it is to talk about directed line segments. PA goes in one direction, PB goes in the other. So because they're in opposite directions, one of them is actually negative. Okay. Another way to explain it without using directed line segments, what's one of our other formulas for power of a point? We've got the one with the tangents, but you can't talk about tangents when you're inside the circle. What's the other formula that we have?
O squared minus
So
R squared.
PO squared minus R squared. And this formula doesn't care whether you're inside the circle or outside the circle. So if PO is inside the circle, so if PO is there, PO is smaller than R. So that's what happens when you're inside the circle. So PO squared is less than R squared. Cool. Just thought I'd mention that. Okay, so last cool thing with radical centers and axes. Let's say you've got 3 circles and another one over there. Okay, what is the radical axis of these 2 circles? Where is it? So we know it's a line that's perpendicular to the line between the centers, but like, is it more on this side or more on that side? Or is it like in the middle?
Now I'm showing you where it is. It's more on that.
More on this side.
Yeah.
Okay. Basically, because the bigger circle is bigger, it's actually closer to the bigger circle side. The reason being that you can be close to the big circle and still have tangents that are big. Remember that the power point is also equal to the square of the distance to one of the tangents. So if you're close to the big circle, you can still have long tangents, and then kind of long tangent to the smaller circle. Cool. So that's the one radical center. There we go. Line there. It's going to be very close to this one because this one's very big. And yeah, that's not going to work. Something like that. So there's your radical center, which is a point. It's not a triangle. There's a point. Okay, cool. Do we have any questions about anything? Radical centers, triangles, lines. girlfriends. No? Good. What time is it? 15 minutes, 15 minutes, 15 minutes. Okay, centroid, circumcenter, incenter, orthocenter. Okay, pick two.
The first
Actually, let's pick one first and then we'll pick another one later. Okay, I've got circumcenter, orthocenter, centroid. Like, does no one want the incenter? Shame. Okay, let's stick hands up for centroid. You can vote only once. Okay, we got 2 hands for centroid. Another one, circumcenter. 5, 6. Someone picking their nose. Okay, that's 6. In center. 1, 4. Okay, 4.